All right, so this video we're going to solve a problem where we are fully factoring a given polynomial, and in particular for this problem we're going to be doing this by necessity, but we're going to be using primarily rational root theorem and the synthetic division, so we can practice those skills as well. Okay, so this problem, right, we want to fully factor and we're given this long polynomial. So given this giant polynomial, remember when we have to factor a polynomial, rational root theorem is always the last resort. It's basically a way of doing educated guessing, and that is really sort of the worst thing to sort of have to resort to. Nonetheless, there are times where you don't have a choice. So first thing I'm going to do when I look at this is ask, okay, are there any sort of quadratic tricks I can use? Is this a quadratic form? So remember a quadratic form, that would be 3 terms, and they would have sort of the highest power is twice the middle term's power, and then we have a constant. Clearly this is not 3 terms, so already I can tell this is not going to be any quadratic form I can deal with. The only other option would be factor by grouping. So in order for it to be factor by grouping, it would have to be some non-prime number of terms. So I'd count them 1, 2, 3, 4, 5, 6. That's promising. I could try to factor this into either 3 groups of 2 or 2 groups of 3. But if I look at this, it's sort of relatively clear, or maybe hopefully it will be quickly clear, right? If I try to do 2 groups of 2, say like this and this, there's no way I'm going to factor something to make -4 into -55, because the leading terms are already the same number, except for this one's negative. If I try to do a group of 3, like these 3 and these 3, the middle term is the biggest, the middle term is not the biggest here. So you could try a few groupings, it turns out it's not going to work. So really, without grouping, without any kind of quadratic form stuff, we're down to rational root theorem. So remember rational root theorem. So I'm going to abbreviate it with RRT, rational root theorem. That says that we want to take the factors of the last number and divide by factors of the first number. So the good news is factors of the first number, just 1. So that's that, at least, right? Bad news is factors of this last number, there's kind of a lot, right? So we can go through and list them. In fact, so obviously we're always going to have 1 as a factor, right? Because 1 goes into everything. So I'm just going to write out, just to be sort of very clear this first time, factors of 1 from x to the 5th, that's just 1. And factors of 195. So factors of 195, you can do this by doing the prime number tree, right? So that's the doing 195 and splitting it as you can sort of think of factors to split with it. I'm going to write them out for the sake of sort of time in the video. So 1, always a factor. Clearly not an even number. 2 is not going to be a factor. 3 is going to be a factor because if we add up these digits, we get something divisible by 3, right? So we get 15. 15 is divisible by 3. So 3 is a factor. Last number is 5 or 0, so 5 is a factor. So in particular, 5 is going to multiply against 39. So I guess that means since 39 is divisible by 13, 13 will be a factor. And then 13, so that's going to go into that once, leaving 65, so that's going to be 15. And now I'm getting that as a pair, so the next pair, this is going to be 39. Against 3 is going to be 65. And against 1 is 195. Okay? So possible zeros according to the rational root theorem. So possible zeros. So I'm going to have plus or minus. All of these divisible by 1, so it's just these things. So 1, 3, 5, 13, 39, 65, and 195. Okay? So here's my possible zeros. Now, I can plug these in up here and see if I get 0. As mentioned, though, if I'm going to compute a polynomial, and we mentioned this in the video on synthetic division, right? I could plug in 65 to the 5th power and try to figure that out. It would obviously be a nightmare. Even I would be like, no, right? But instead, what I could do is use synthetic division to plug that in and see if I get a remainder of 0. If I get a remainder of 0, it will also give me the polynomial that happens when I factor it out. So it does everything I want all at once. So if you're using rational root theorem, you pretty much always want to be using synthetic division or polynomial long division if you're more comfortable with that. Either one is fine, because it will sort of kill 2 birds in 1 stone. It will tell you whether or not it has a remainder of 0, which tells you whether or not it's a root. And if it does work, it will already give you the result of factoring that piece out, which you would then have to do next anyway. And it's typically an easier way to compute what the value is when you plug in some annoying number like 65 here. Okay, so for the sake, again, of time for this video, I'm not going to sort of demonstrate what happens when you keep choosing wrong numbers. I do want to stress, though, to keep in mind that it is perfectly normal that you would guess a number and it doesn't happen to work, and that's just bad luck. Clearly, I know how this is going to factor eventually, so I'm going to choose one that works, but it's by virtue of the fact that I already sort of cheat and know ahead of time. So it's perfectly fine to try different values, and you'll sort of discover that they don't work, and then you just try another one, which is why rational root theorem is pretty terrible, because sometimes you have to try a lot of things before you get there. Okay, so here I'm going to try 5 as a 0. So remembering how we set up our synthetic division, I'm going to have 5. I'm going to have my little grid, and then I'm going to write down the coefficients along the line here. So I'm going to have 1, -4, right? -1, -55, 136, and 195. There are other numbers that work. This is just the one I happen to be using, so sorry, one sec. That 5 came out pretty terribly. Let me fix that. So 195. So as I said, there are no other numbers that work. This is just the one I'm picking. And then I have my little bottom line down here. First step, I'm going to drop the 1. And then remember, I'm going to take the 1, multiply it against the number up here, so multiply it by 5, and write it up here. So 1 times 5 is 5. Add straight down, I get 1. 1 times 5 is 5 again. Add straight down, I get 4. So this is nice, right? Because before I'd have to do 5 to the 5th, right? If I wanted to do this, I'd do 5 to the 5th, and I have to multiply all of that out. But this is actually giving me sort of an ongoing cancellation that's keeping the numbers somewhat manageable as I go. So 5 times 4, that's 20. Add straight down. Of course, I say that, and now I'm going to get -35 times 5. Still, that's a lot better than doing 5 to the 5th. So it doesn't stay perfect, but it helps. So -35 times 5, so that's going to be 150 plus 25, so that's going to be -175. Add straight down again, so this is going to give me 39. Negative, right? And then -39 times 5, so that's going to be -40 times 5 is -200, less 5, so that's going to be -195, which gets me 0. And this is good news, right? Because a remainder of 0 means that it goes in perfectly. So what that tells me then is that 5 is a 0, which means x minus that number, so x minus 5 is a root. And what is left over here is a leftover polynomial. So that leaves me with, so remember I'm going to drop all my powers by 1, synthetic division. You can also do it by going backwards. So this is the remainder, the constant, x, x squared, x third, x fourth. So I'm going to get x to the 4th. So that's this one, plus x cubed, plus 4x squared, minus 35x, minus 39. Okay. So thanks to rational root theorem, I got a potential 0, which worked. And thanks to synthetic division, I was able to then write this as a product of two polynomials, right? So I've factored it once. Now here's the important part that is sort of one of the key parts that is often overlooked, and this is what leads to not necessarily wrong answers, but spending many times longer than you need to be on solving this problem. The key here is once I've factored something out, treat this new thing as a new problem. So my goal now is to fully factor this piece, and this thing will tag along for the ride. So I even want to, I mean, you don't have to write this part, but I'm even going to write out because I want to think of it as saying, okay, sort of problem part B, right? And then I'm going to say fully factor this thing, x to the fourth plus x cubed plus 4x squared minus 35x minus 39. The point here being that I really do want to think of this as a whole new problem. So I go through the whole initial steps that I mentioned earlier, right? First thing I do I have any quadratic form things I could use? Well, it's not 3 terms, so that's certainly not going to work. I should clarify that some quadratics can form pieces, even most of them, under the right circumstances, can be used on 2 terms as well as 3. So when I say 3, I really mean 3 or less. Nonetheless, it's not 3 or fewer terms, not less, fewer, right? So I have 5 here. Moreover, grouping is certainly not going to work, at least not obviously, because I have a prime number, 5 is prime, so I have a prime number of terms, so trying to factor that with grouping is almost certainly going to cause a bunch of problems for me. So I'm again down to rational root theorem. But, and this is where I want to stress this, I'm not doing rational root theorem with this list anymore. This is a new problem, right? I mean, it's not really, it's part B, but this is I'm trying to treat this as a new problem, which means I want to generate a new rational root theorem list. So in particular, rational root theorem, I still have the coefficients 1, but now I have a coefficient of negative 39, so I'm doing the factors of the negative 39 or positive 39, doesn't matter because I'm going to do plus or minus. So I have factors of 39 and factors of 1. So if I take things here divided by 1, I'm just going to get these factors, which are 1, 3, 13, and 39. So I want to point this out because here I had, right, 1, 2, 3, 4, 5, 6, 7, plus or minus, I had 14 things to choose from. Now I have 8, right? So just by making sure that I'm only looking at the leftover piece, I've cut out 6 possible factors immediately that I don't have to worry about. And it's not obviously, I mean, I cut out 6, it can't be just 1, but it's not just the 5 that I found, right? 65 is no longer there, 195 is no longer there, I don't have to check these gigantic numbers because I know they're not gonna work, right? So it is very worthwhile to build a new list if you changed the numbers that were here, right? So here they were 1 and 195, here it's 1 and 39. Since they've changed, I will get a smaller list. You should also note that this list should be a subset of this list, right? So I'm going to be testing plus or minus these things, and all of these things appear on here, right? 1, 3, 13, 39. But I am now missing some, 5, 65, and 195. I no longer have to check those, okay? All right, so again, you would sort of test whatever it is that you are wanting to pick. And again, I'm going to pick numbers that happen to work for the sake of time. But we do this the same way we did it here. So here I'm going to choose 3. And again, I'm going to write the coefficients all the way down, making sure I account for every power, but all the powers are represented here. So I'm going to have 1, 1, 4, negative 35, and negative 39. Write my bottom. drop the first one, and proceed, right? So I'm going to do 1 times 3, that's 3, write it over here, and then add down. That gives me 4. 4 times 3 is 12, add straight down, that gets me 16. 16 times 3 is 48, add straight down, so this is going to be 13. 3 times 13 is 39, add straight down, that gets me 0, which again is exactly what I'm hoping for because that means that the remainder is 0, so this does in fact factor. And that tells me that my original, which is now, remember, this subpiece, is going to be, this is a 0, so x minus 3, right? Because that way, if I plug in 3, I get 0. And then I'm going to have, so again, I'll have 1 fewer power, or I can work backwards. So remainder constant x squared, x cubed. So x cubed plus 4x squared plus 16x plus 13, 0 remainder. And it is a good idea, so this is equal to that. But remember, the whole thing I'm trying to get is this thing back at the beginning, where I had already factored out a term. So it's a good idea to sort of include this to make sure you're keeping track all the way through. So I also have this x minus 5 that I had factored out earlier, right? So I had already factored it out. I was sort of ignoring it because I was only doing this piece right here. And so I did this piece, I factored that into this thing, and then wrote this there, okay? And now, again, I want to think of this as a whole new problem and try to solve it again, okay? So with the power of magic, I'm going to reset the board a bit and copy this so that I have room to keep going. So abracadabra. So I probably teleported, but you know, I'm a magician. So we factored this twice so far, and that leaves us this piece. And again, just like before, so before we did like part B and we tried to do just the remainder, we're gonna do the same thing. So we're gonna ignore all the stuff we did before, look at just this and say, okay, what can I factor? What methods can I use for that? Again, I could try quadratic pieces, but this is 3 terms, so that's not, sorry, this is more than 3 terms, so that's not gonna work. I could also try to do factor by grouping, which this at least seems a little more plausible, but it turns out when we try to do that, right, so I'd have the second coefficient has to be 4 times more. That's not going to work there. Those two also not going to work. So it turns out grouping doesn't work either. So once again, I am down to my oh so lovely friend, rational root theorem. I'm going to use a slightly different color here because why not? So rational root theorem. But again, I'm not using any of my old lists. I'm going to generate a new list. And that's a good idea because I have different things again, right? Different coefficients. I have still 1 in the front, which is good, but now I have 13 instead of 39 or 195. So my rational root theorem then is going to come down to 1 or 13. For those of you following along at home, the next one I'm going to factor out is honestly what I probably would have done the first one, the first time around. So here, I'm going to factor out a 0 of -1. So that's going to be the factor x plus 1. But what I'm going to have then is -1, which again I'm picking because I know it's going to work. But usually when I've sort of been given a whole piece like this, the things I normally choose first are plus or minus 1 because they're very quick and easy to compute. So I would have done this much earlier, but I wanted to emphasize what happens if you pick numbers other than 1 or -1, how it reduces the rational root theorem list very nicely. I'm going to choose -1. Again, I'm going to have the coefficients written underneath. So I have 1, 4, 16, and 13. Write my little bar underneath. Drop the first one. And then I'm going to multiply, right? -1 times 1 is -1. Put over here, add straight down, that's 3. Multiply, that's -3. Add straight down is 13. Multiply, -13. Add straight down, 0. again, good news because 0 means no remainder, all right? So that means that if I pull out a 0 of -1, which means it's going to be, so this 0 means that I'm going to have, I'll be pretty close to done, so I'm going to write it over here. So 0 of -1 means I'm going to have x minus -1. So I could write that as x plus 1, but I'm just emphasizing that it's x minus this number, right? And then this is what I have left over. So I'm going to have, and again, I can do this with subtracting 1 from the thing or going backwards. If you couldn't tell, like to go backwards here. So I'm going to have remainder, constant x squared. So I'm going to have x squared plus 3x plus 13. And just as a reminder, and really I could write this in front or afterward, I'm going to include the two factors that I've already found. So I have x minus 5 and x minus 3. Okay, so all put together, what I'm going to end up with then is x plus 1, x minus 3, x minus 5, and x squared plus 3x plus 13. And now I am, once again, going to look at just the remainder as its own problem and ask, okay, can I factor this thing? Now, hallelujah, right? I have 3 terms. This is clearly a quadratic form, right? So I have twice the power on the first term as I have in the middle, because this is 1 times 2 is 2. This is clearly a quadratic equation, which means I definitely should not be using, under any circumstances, rational root theorem, because there are just way other better ways of dealing with quadratics. But keep in mind, if I'm factoring over the real numbers, which is what I'm doing here, then it is possible that I actually can't factor this anymore, right? So at every previous stage, say here, I know I can factor these because the highest power that I should ever have in a fully factored form is 2. But that doesn't mean that if I get everything to degree 2, then I'm done. It just means that it's a way of telling if I definitely have more work to do, or if I need to see if I have more work to do, right? So here, because this was higher than degree 2, I definitely needed to do more. So I went with rational root theorem. Here it's possible that I might have to factor this, like this might actually factor with real values, or it might not, in which case I'm done. So the question is, how do you know? So in order to know, we're going to use what's called the discriminant, right? So this is in the quadratic formula tile on Chronos, as of the writing of this, or recording of this anyway. But the discriminant of a quadratic is essentially the piece that's under the square root when you're doing the quadratic formula. So it's the, if you remember the quadratic formula, under the square root you have b squared minus 4ac, where this is of the form, right, ax squared plus bx plus c. So I'm going to look at b squared minus 4 times a times c. So I'm going to have 3 squared minus 4 times a, which is 1, times c, which is 13. So that's going to be 9 minus 4 times 1 is 4 times 13 is 52. So all I actually care about is whether this thing is positive, negative, or 0. So it's clearly not 0, and I'm subtracting a bigger number from a smaller number. This is clearly less than 0, right? So if the discriminant is less than 0, then hopefully we should know that that tells us that there are no real solutions, meaning there are no real roots, real valued roots. So if I were to factor this, the only way I could factor it is with complex numbers, which is not the goal. So this then is fully factored, which means this whole thing, because any linear piece is fully factored already, this whole thing is fully factored. So my problem to fully factor this is my solution. Okay? So again, as a recap, each step of the way, we tried to do anything we could to avoid rational root theorem. in this very particular problem, that never ended up working out. I will emphasize that there are many times, many times, where that will work out. So you absolutely want to take the 3 seconds it took us to look at it and go, okay, can I do any quadratic form stuff? No. Can I do any grouping stuff? And doesn't look like it. No, I can't. Okay, now we have to do rational root theorem. Then you go through this, right? And each time you did the rational root theorem, if you had to do it again, you did it on just the remaining piece and rebuilt another rational root theorem list, because that sort of systematically carves down the amount of problems, the amount of pieces that you have to check, okay? And then finally, we got to the point where we actually did have a quadratic left, and we sort of didn't obviously see a way of factoring it, right? It wasn't like a very clear, obvious factorable thing. And so we checked using the discriminant. We found the discriminant was less than 0, so that tells us that it's already factored over the real numbers. And thus, this is the fully factored, meaning none of these individual multiplicative terms, this thing, this thing, this thing, this thing, none of these pieces can be factored fully, factored anymore. So this is the fully factored form of this thing. And that's it.